Hey everybody, welcome to the second part of our very long lecture on solution making. I know that it seems kind of like a lot to watch, but there are a lot of potential questions that they could ask, and you really need to be solid with molarity to be able to kind of answer a lot of those questions. So that's why we are hitting them so hard. So example number 1 said to explain how you'd make 750 milliliters of a 2.35 molar KOH solution. And we are going to assume in this problem you have a 750 milliliter volumetric flask. They would tell you in the problem what you would be able to be using for glassware, and you're always going to pick the most precise possible. So if they give you something crazy like, oh, you only have a graduated cylinder to use or a beaker, you're going to use the graduated cylinder because it's the most precise piece of equipment. But we'll assume in this case you've got a volumetric flask that'll work out for you. So the first thing we're going to need to do is we're going to need to figure out how much KOH we are going to need to make this solution. And when they say like explain how you do that solution, it's always math. You don't need to actually explain the math. You just show the math and then that's fine. So if I want to figure out how many grams of this KOH I'm going to need, the first thing I have to do is figure out moles of KOH. And like I told you before, if you take molarity times volume, you are going to always get moles. Now the kicker with this is that it has to be in the same units. So this is milliliters here. Molarity, if you remember, is in moles per liter. So you've got two options here. You can either convert 750 milliliters to liters, and that's easy enough to do, or I'm going to show you a little shortcut that I like to do because I don't sometimes feel like converting. So if I take my molarity times my volume, and I'm going to write my volume first because it's not a conversion factor, so it doesn't really matter which way you write it, but this is my personal preference. If I have 750 milliliters of solution that I'm making and I want to multiply it by my molarity, I'm not going to write it as moles per liter. I am going to write it as 2.35 moles of KOH, okay, divided by 1,000 milliliters. That way my milliliters cancel out. Now, a couple things that I see people screwing up with this. We're not even like done with the problem, but things I see people messing up with is that they put the unit 2.35 m per liter like that. That's wrong. Units are incorrect because this is moles per liter, okay? I see people going like this, and then they think that the liters are on the top, so then they try and put the 750 milliliters on the bottom, or they'll do a weird flippy thing, or they'll have 750 milliliters, or they put it into liters or whatever, and then they would put the 2.35 moles per liter on the bottom because they think that they cancel out. But when they write the slash like this, remember that the L is a denominator. So if I have moles per liter, it's moles over liters, or in this case, moles over milliliters. So if we come back to, I'm going to get rid of this so we're not getting confused. If you come back to this, the reason why I put 2.35 moles over 1,000 milliliters so that I don't have to convert this unit. If you want to convert this to liters, you would leave your molarity as moles per liter. It is going to be the same. It doesn't really change anything. And if I multiply these two things together, you can see that the milliliters cancel out and I get moles for my answer. So that's where we're going from here. Now you could get the moles and then convert them directly to grams, but I'm going to just do it in kind of one fell swoop here. So I'm going to put the molar mass of my KOH, which is 56.108 grams for every 1 mole of KOH. And then I'm going to do my math for that. So 750 times 2.35 divided by 1,000 times 56.108 into my calculator, and I get 98.89 grams of KOH that I need. Think if this makes sense to you. So if I'm going to make a liter of solution, I would need 2.35 moles, and each mole weighs 56 grams. So I'm going to need, in theory, if I make a liter of this, over 120 grams of stuff, but I'm not. I am only making 3/4 of a liter, so it makes sense that I'm not going to need over 100 grams of this, and it always helps to see if your answer actually makes sense in the context here. Okay, so it asks to explain how you're going to make that solution. So I would just put in a little procedure. So I would say weigh out 98.89 grams of KOH. Okay. Then I would add them to a 750 milliliter volumetric flask, and I'm just going to put vol flask there. Okay. Then you are going to add, and probably deionized water. Deionized water is run through a filter and it takes out all the extra ions that could potentially go in and have like a side reaction. So you're going to add deionized water and fill flask halfway, and then I'm going to put dissolve solid. Okay. Then we are going to fill the flask to the line with deionized water, and then you are going to cap and invert to mix. Okay, so if they walk you through and ask you for how to make the solution, you show them the math, then you explain how. In the past, I have had students talk about like they literally write sentences that says 750 milliliters times this, and they wrote this out in words. They don't want that. This math is support enough for the mass. You just need to explain how you actually do it. Okay, so that is the example for making stuff from a solid. Now, the second question I'm going to give you guys is the one from making something from a previous existing solution. So if you read through this problem, it says if 45 milliliters of water are added to 250 milliliters of a solution, what will the molarity be? So if you think about it, you have a beaker here, or volumetric flask, or whatever the heck you want to call it, and it has 250 milliliters for its current volume, and it is 0.75 molar. If I add into here 45 milliliters more water, it's going to make this concentration go down. And to figure out our new concentration, we can use M1V1 equals M2V2. So like I said before, it doesn't really matter what we pick as our M1 and our V1. It's not going to make a difference. What I tend to do is I tend to think of this first one as my original solution, and then my second one as my new solution, because then I'll be able to kind of figure it out. But you got to be really careful when you read to fill these out correctly. So I've got M1 and V1 equaling M2 and V2. So my original solution before I changed it or added any water to it is 250 milliliters for its volume, and its concentration is 0.75 molar. So my M1 is going to be 0.75 molar times, and I told you before, the units aren't important in this problem as much because the molarity and the milliliters here are not going to have to cancel each other out, because in our new problem here, we are looking for the new molarity. We don't know what that is. And our new volume, if you think about it, is 250 plus another 45 milliliters. So that's 295 milliliters. Now, units aren't important because of this math I'm about to do here. I want to isolate M2. So I'm going to divide by 295 milliliters on both sides. Okay. And if you look here, the units of milliliters cancel out, and I'm left with molarity. So it's not necessarily super important to have the units in liters in this problem, because it's going to cancel out either way. So what I'm going to do is I'm going to take 0.75 times 250, and then I'm going to get 295 in my denominator. When I do that, M2 comes out to be 0.636 molar. Stop and take a second to see if that makes sense. I started off at 0.75 molar. If my concentration doesn't go down for my second answer, I did it wrong, because if I add more water, the concentration is going to go down. The way that this equation works is that the moles from my original solution are still the same even though I have more of a volume. So what's happened is, in this case, my molarity went down and my volume went up, but the total moles in my solution stayed exactly the same. Okay, so this is one problem. This is not so much for the solution making, but the other part. And here's the last one. How much 2.8 molar HCl would need to be added to make 750 milliliters of a 1 molar solution? So this is more the type of math that you're going to see. So when I read through this problem, I recognize that I'm starting with a molar solution and I need to make a different molar solution. So that's how I know I'm going to use M1V1 equals M2V2 here. And again, it's not necessarily important which one goes in the 1 and the 2, but I like to think of it as my original. So it's 2.8 molars what I'm starting with. Okay. And I do not know how much of that I am going to use for my solution. That is equal to my new molarity, 1 molar, times what I am going to need to make, which is 750 milliliters. And you say to yourself, Mrs. Ottmeyer, this is still problematic here because this milliliters is going to be a problem. It won't. So now I've got to isolate and get V1 by itself. To do that, I'm going to divide both sides by 2.8 molar. And in this case now, the molar cancels out. And so then I'm still left with units of milliliters and not going to lose any sleep about it. So when I do the math, I'm going to take 1 times 750 divided by 2.8, and I am going to get 267.85 milliliters. Now, if you look at the numbers that we start with in this problem, I've got 2.8, I've got 1.0, and I've got 750. All three of these things have 3 significant figures. This 0 here is just a place holding 0. So my answer, in theory, should be 270 milliliters. Now that's crazy for making a solution. So realistically, I should have written this problem a little bit more carefully. And then I could have just said 268 milliliters. Okay? So hopefully this makes sense. If you have any questions, please make sure that you get those cleared up and we will talk about them as soon as we can. Good luck!